Hello and welcome to the introduction to Rocksolid Graphics SDK. I'm Francesco Balestrieri. I'm head of products at Basemark. And with me today we have Timo Tossavainen, chief engineer, Seth Nykamp, senior technical artist, and Mikael Korpela, lead developer. And we're going to start with an introduction to Rocksolid, where it comes from, and what are its main features. And then Timo will talk about the graphical features in more detail and show some demos of content created with Rocksolid. And finally, Seth will give a walkthrough of our Blender workflow, which we use internally to develop our content and that we are going to release soon as part of the SDK package. At the end, we're going to take questions. Feel free to write them in the chat at any time, but we'll address them all once the presentation is over. First of all, a few words about Basemark. Basemark was founded in 2015 in Finland, and it has a long experience in the automotive sector through our product development and professional services. We are also a leader in GPU benchmarks. You might be familiar with our Basemark GPU mobile and desktop benchmark that you can download from our website and from the different application stores. And we also created the first automotive-specific graphics benchmark called BATS, Basemark Automotive Test Suite, that focuses on use cases and graphics techniques used for automotive HMIs and similar. And all of these benchmarks and the upcoming ones are powered by the same engine, the Rocksolid engine, which is made available through the SDK that we are talking about here, and includes all the learnings that we have taken from the development of these benchmarks and from our automotive work. In our experience, some of the toughest challenges when developing real-time mission-critical applications are, first of all, optimizing for power consumption, especially in an embedded environment. Power consumption is, of course, important, and in a car, it can mean excessive power consumption can mean reduced range in an electric vehicle or increased consumption in a regular one. But at the same time, superior graphics are now a key selling point. It's what the user often sees when first entering the car. Cars are becoming more advanced. There are assisted driving use cases that require 3D visualization, things like park assist and displaying the surroundings of the car, not to mention augmented reality, HUDs, and so forth. So there needs to be a balance between the available graphics features and the power consumption mentioned earlier. And then finally, when moving from one product generation to the next, it's important to be able to migrate to a new hardware platform with as little cost as possible, to avoid being locked into specific vendors and being able to take advantage of the best price-performance ratio. Rocksolid helps in all of these challenges. It's a cross-platform graphics API agnostic graphic solution. It's optimized for small memory footprint and fast startup times. It's portable across different hardware platforms and helps eliminate or at least reduce the SoC vendor lock, and makes the migration to new hardware easier. And it's developed with automotive requirements in mind that we have learned from our automotive work and that we continue discussing and defining with our automotive partners. Talking about performance, I mentioned a few times that Basemark has a long experience in benchmarks, and of course, when developing benchmarks, performance is of the utmost importance. The software has to get out of the way. You don't want to benchmark your software, but you want to benchmark the underlying drivers and hardware. And we have worked with GPU vendors and SoC vendors to ensure that we use the most up-to-date and advanced techniques that squeezes everything possible out of the hardware. We're particularly proud of our Vulkan renderer, which helps us achieve high performance, maximum performance, and which we measure to be higher than incumbent automotive HMIs, sometimes as much as 130%. Rocksolid is portable. It's, as I mentioned, cross graphics API. It works on Vulkan, OpenGL, and OpenGL ES, and even DirectX and Metal. It's also working on different operating systems. We support various flavors of Linux, including Yocto, Android, Windows, iOS, and OS X. And it runs on a variety of hardwares, automotive grade, mobile, and desktop, some of which are listed here, but many more have been tested and verified. Finally, Rocksolid is developed with automotive requirements in mind. We have features that come specifically from our automotive experience and automotive benchmark requirements, such as optimized render layers and composition, as well as multi-screen support. And it's developed with safety in mind, and we are pursuing certification at various ASIL levels during this year. But of course, all of these features are not very useful if you can't integrate Rocksolid into your development workflow. Our philosophy is to integrate with existing tools rather than provide our own. Internally, we use Blender, like Seth will demonstrate in a moment. We like Blender. It's open source. It's fully featured, and it works very well for us. And it lets us create advanced 2D, 3D user interfaces. But of course, we recognize that it may not be the only tool that people prefer out there. So any content creation tool that can generate the standard GLTF format can be used with Rocksolid. In terms of application development, Rocksolid applications are C++ applications, at the moment at least, and the Rocksolid libraries integrate seamlessly with different IDEs, such as Visual Studio and Eclipse. Rocksolid supports iterative development of user interfaces. Thanks to its cross-platform nature, you can run your content on your desktop using the Rocksolid engine and then transfer it to the device on the same engine and see the same rendering on the supported hardware. Rocksolid is under continuous development. We're adding features all the time, and something that is going to appear soon are more effects and pipelines. We are working on a ray tracing pipeline that at the moment is used in our upcoming benchmark that Timo will show pretty soon. We're also working on a safe rendering pipeline for ASIL certification, and we have developed a similar concept. Excuse me. We have developed a similar concept for cross-platform heterogeneous computing on GPU or other accelerators, which we call Rocksolid Compute. That brings the same benefits, basically, but for compute use cases, which are increasingly important in the automotive space. Okay, so that was the introduction. Again, if you have questions, please write them in the chat. And I now hand it over to Timo to talk about the Rocksolid graphics features and show some examples.
Thank you. So I'm going to talk just briefly about how our software works to achieve what we do in our benchmarks. So in the benchmarks, we compare different graphics APIs, so we need to be able to benchmark different graphics API driver implementations against each other, and then also compare different hardware used, for example, in cars or on the desktop to each other performance-wise. And of course, this is quite challenging because the comparison has to be fair, so we need to be able to show comparable content and comparable workloads on all of them, and that means that there are some challenges in implementing this in software. And also to make the benchmarks relevant, they have to be able to get most out of the hardware. So how do we do that? So underlying the benchmarks is the Rocksolid graphics engine. And how the engine is actually set up, it's a layered architecture. So on the very bottom of the architecture is a graphics API abstraction layer that we call RSGFX. And how RSGFX works is that there is a graph-based API to define all the rendering operations needed to form the image, and it's been designed so that we can feed modern graphics APIs such as Vulkan and DirectX in a way that the hardware can then optimize the execution, and we can also optimize the resource usage while doing the rendering. Of course, low-level API such as RSGFX is not that useful by itself. So on top of that, we have a customizable renderer that we call RS Renderer. And it's more like a framework for renderers. So you can make your custom rendering pipelines for your own application. We have a number of standard pipelines that are used in the benchmarks, for example. So the standard pipelines are using forward plus rendering, which is familiar from computer games nowadays. And the pipelines, in addition, are based on physically based rendering with image-based lighting. Some of the more modern techniques that we've recently included contain ray tracing. I will demonstrate that in a moment. And then there's a number of rendering techniques that are available out of the box that you can use to make a custom pipeline. Of course, it's totally possible to implement also custom rendering techniques if that is desired. And actually what is happening is that when we are trying to keep our benchmarks current, we are all the time experimenting with rendering techniques that appear in modern games, for example, and then they are incorporated into Rocksolid. And of course, realistic graphics needs a lot of different types of techniques. I mentioned rendering techniques in the previous slide. There are also post-processing techniques such as which are mostly image-based, such as bloom, anti-aliasing, depth of field, and so on. And those are also available out of the box. Of course, rendering itself is not even sufficient, but somehow you have to be able to manage the scene or the graphical content. So there's interaction, typically animations, basically managing the 3D world that you want to show the users. And for that purpose, we have a modern data-oriented scene management system, which we call RS Scene. It's based on the entity component system model. And in it, you can, for example, implement keyframe animation. Well, skinning it's kind of also included in the renderer techniques, and it has support for events. And basically, all the application logic can be written then on top of RS Scene by to modify the scene parameters, which are then reflected in the rendered representation of the scene. But even this is not enough, because in the end, you want to have your own content. And for that purpose, we have asset import from different modeling tools. We call it RS Loader. The typical asset pipeline is to use, for example, Blender, and then export to GLTF, which can be then loaded to Rocksolid. And as Francesco mentioned, we will demonstrate that, or Seth will demonstrate that after I'm done. And finally, of course, there's a number of utilities, like how do you set up rendering windows, how do you handle input. Sometimes you need a bit of math routines to do, for example, intersection calculations. So we have a small collection of those also included in the Rocksolid SDK. But now let's go and look at some of the demos that show how Rocksolid actually scales from fairly simple graphics to modern game-level graphics. So first we have here an example of kind of an entry-level instrument cluster. This one has been rendered on an SoC using OpenGLES. So the content is mostly 2D, but animated, and there's anti-aliasing and similar things. So you could find this, for example, in a car. Next one is a bit more advanced, so kind of similar instrument cluster, but more 3D content, a bit of actually entertainment content also, and more elements and layers visible. Also running on an SoC, and this one is rendered using Vulkan. And then finally, an example of our up-and-coming GPU's benchmark, which is intended for actually high-end graphics cards. And this is a bit of a work in progress, but shows some of the more advanced rendering techniques that Rocksolid nowadays supports. So here you can see a bunch of mirrors that have been rendered using ray tracing. And for example, we've also included volumetric lighting. And this is rendered using DirectX. Okay, and so that was my part about Rocksolid graphics. And next, Seth will show you how to create models and content with Blender and run it in Rocksolid. So go ahead, Seth.
Hi, I'm Seth Nykamp. I'll be demoing off the Blender to Rocksolid pipeline. So far, I heard a lot about Rocksolid's capabilities from Timo and Francesco. Let's see how we can prototype designs and build out real-time ready assets for Rocksolid. All right, so here we are in Blender. And what here we are in Blender, and what we're gonna implement is this low-end cluster design from the BATS graphics test. So this is a 1920 by 720 image. And the origin starts up here at the top left-hand corner. I'd just like to replicate what we see here in Photoshop and represent that in Blender. So let's go ahead and do that. I'm gonna delete out these elements that are unnecessary. I'm gonna go ahead and position the camera. And then I'm going to add in the image that we saw in Photoshop. I'm going to change this image so that 1000 pixels equals 1000 Blender units. And from that image, it generated a polyplane to that dimension. So let's go ahead and add in some more elements. And let's set our units so we can start working in pixels. And I'll turn on a way to see everything in the viewport. Okay, now we can work in pixels, and I'm going to move everything over half and down half. I'm going to set this camera resolution to 720. A little bit larger than what I was expecting there. So, okay, and then we can move this camera over the same way we did with the image. All right, now we have the camera almost all set up. We want to put it in orthographic perspective and set the aspect ratio. So the next step is to set up our materials so we can start using them in Rocksolid. So to set up the materials, I'm going to go ahead and select these objects, add in an emission shader. I'm going to copy this setup and do the same thing for each element. I'm going to set the material properties as well. In this one, I would like to do something different. I want to separate out its RGB value and drive the red channel of this image as the alpha. And I'm going to set this to black, as this mesh is going to act as a mask. I'm going to set this background image to opaque. It's going to be an opaque shader. That way we're not rendering any more transparency than necessary. Set everything with backface calling. Okay, now let's go ahead and set up our rotation values. We're working in quaternions. I'm going to put it in Euler. And now I'm going to rotate from negative 119 to a positive 119 for the 0 to 240 speed range. So let's add in a couple properties here. I'm going to set the speed range to 240. So now it goes from 0 to 240, and now I want to map this 0 to 240 custom property to control all the other elements. So the rotation and everything should be controlled through the speed parameter. So let's go ahead and set that up. I'm going to add in some attribute inputs and some attribute outputs. And what I'm working in now is called animation nodes, and this is a visual scripting program. So this allows me to set up logic and cache that data. I'm going to add in a transform object output, and then we'll need a map range node. I'm going to add this in here. I'm going to duplicate that range and add it there. I'm going to copy this data path, add it here, and then we want to rotate this object y coordinate or angle. And we're going to be using degrees. So from 0 to 240 is our range for the speed. And then what we want to do is, as we move from 0 to 240, is we want to go from negative 119 to a positive 119 for the rotation. And then for this sweep value, we're going to go from 0 to 240 back down to 0 to 1. So we're going to remap it to a 0 to 1 range. Okay. So now let's hook up. So now we can see that through this custom property, I'm controlling 3 different properties now. So let's go ahead and hook up the materials to the sweep attribute. And to do that, I'm going to add in a UV map. I'm going to separate its component. I'm going to go ahead and add in a math node and set it to a less than. I'm going to plug that x coordinate into a less than node and make a multiply node, add the alpha, multiply the alpha of everything else, and then plug that into the alpha channel. So now I have control from 0 to 1 as the full range. So all we have to do is drive that property. Okay, and let's go ahead and copy this as driver, go back to our material, and we'll just paste it. Let's hook up the other material too, and that's these side edges here. We'll do the same thing, and then we'll paste it as driver. So now we have all 3 systems now running off the speed parameter, like you would in a normal instance of a car. So let's go ahead and set some keyframe values. Okay, let's jump back over to animation nodes and cache all this data. As there's no visual scripting hookup yet, so we just cache this data. And now let's take a look at what it looks like in Rocksolid. I'm going to put a folder where all these assets and all this information from Blender will be exported to for use with Rocksolid. Okay, so here in Rocksolid now you can see that we have the speed with the comet tail all animating together. One thing that's missing is dynamic text. So let's add in some dynamic text. I'm going to set its rotation to 90. I'm going to go ahead and I'm going to center it with this object's position. So I'm just going to copy its values to this text object. Then I'm going to go ahead and center align it. I'm going to move it forward in the Y. We'll put it on top of everything. Over right there. Okay. Looks okay. You don't really want objects to overlap one another, or else you'll create something called Z-fighting. And what we want to do now is scale this down. Let's make it a little bit more understanding of the kind of information we want to display. And let's give it a different text. I'll give it this one. Okay. Now the next step is to have this register data for our dynamic text. So let's go ahead and do that. The way we can do that is just copy this node, leave that out, rename it to text, and then connect that into the text, and then hit bait keyframes one more time. Go ahead and export. And now we can see we have dynamic text running for our low-end cluster as well. All right, let's do something a little bit more interesting than just that. Let's take a whole nother cluster that wasn't designed with the low-end cluster in mind and combine it together and see how that looks. So I'm going to go ahead and open up another scene. All right, here we are in another scene. This is the high-end cluster. This is our demo. This is our prototype project right now. And what's happening is we have some reflections. We have triplanar projection mapping happening on the buildings. So everything's pretty dynamic. And there's also a force displacement that's happening as well for the camera. So everything is rising to meet the camera in a force perspective. So everything is dynamically displacing. So let's go ahead and just copy this scene. Let's make a new one in our project here. Let's go ahead and paste that scene we have from the other Blender into this Blender project. Okay, now that the scene is merged together, let's hook everything up together. Okay, from this control property, there's a speed value that holds the rate of the car in it. So we'll just take that value and use that instead of the speed that we created earlier, and that'll drive all the rest of the objects that we've already set up. Let's set our range. Okay, and then let's set our resolution as well. And then let's go ahead and bake this data. So as we can see, we're just going through the high-end cluster right now, baking all the data out for the speed to run on these other parameters that we've already set up. Okay, now that's done. Let's go ahead and go back to the other scene, see what happened. So it looks like the speed is different now. So we extracted that information out and put it on to these new properties. They'll drive everything. Now let's combine these two compositions together. I'm going to create an alpha over node. I'm going to now combine both these images together. I'm going to switch this to scene 1. I'm going to take a render of this and render the high-end cluster. Now we can see that they've composited together. And we can see that in Blender as well. And let's go ahead now and export all this data out and compile it for Rocksolid to render. So I just hit the export button. So what's going to happen now is all the Blender files being read, all necessary data is being extracted out to create the materials and hook up the animations to those materials. So that's what's happening now. And this will take a little bit of time. And all right, here we are in Rocksolid now. And now we can see that we combined two instrument clusters that weren't meant to be built together, prototyped out in the same scene, with all the materials and shaders being exported and being run in Rocksolid. All right, that concludes the demo part of the tutorial. Back to you, Francesco.
Thank you, Seth. Great demo. And this concludes the presentation part of the seminar. Oh, sorry, webinar. As I mentioned, the Rocksolid Graphics SDK is available for evaluation. You can apply from our website or by sending an email to our sales team, and they will get back to you asking for more details. And we thank you for joining, and please stay tuned for future webinars that will appear on our website and social media. Thank you, Seth. Thank you, Timo and Mikhail.